Have you ever wondered why apples fall straight down and not sideways or upwards? This seemingly simple question unravels the enigma of gravity, a fundamental force that subtly yet unceasingly shapes our everyday lives. It's the invisible hand that keeps us rooted to the earth, and the silent puppeteer that guides the ebb and flow of our ocean tides. Our understanding of gravity took a monumental leap forward with Sir Isaac Newton's law of universal gravitation. This groundbreaking theory painted a picture of the universe where every object, no matter how big or small, pulls on every other with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. But Newton's law, revolutionary as it was, left some questions unanswered. It didn't explain why light bends around massive objects or how gravity can act instantly over vast cosmic distances. And that's where Einstein enters the scene, altering our perception of gravity forever. Imagine you're standing on a trampoline. What happens when you place a heavy ball in the middle? As you probably guessed, the ball sinks and creates a dip, pulling everything around it towards its center. Now let's swap that trampoline for the fabric of the universe, an intricate blend of space and time, and the ball for a massive object such as a planet or a star. This is the essence of Einstein's revolutionary idea. Einstein's theory of general relativity, published in 1915, proposed a radical new understanding of gravity. Instead of viewing gravity as a mysterious force reaching out across the void to pull objects together, Einstein suggested that gravity is the result of the warping of space-time by mass. Picture space-time as a vast, flexible sheet. When a massive object, like a planet, is present, it distorts this fabric, creating a sort of well. Now, when a smaller object comes near this well, it's like a marble rolling towards the dip created by the heavy ball on the trampoline. It's drawn towards the mass, not because of an invisible hand pulling it, but because it's simply following the curve of the space-time around it. This is what we perceive as gravity. The moon orbits the Earth not because it's being pulled by an invisible rope, but because it's caught in the Earth's space-time well, constantly falling towards it but also moving fast enough to keep missing it. Einstein's idea was revolutionary because it treated space and time as dynamic entities that could interact with matter and energy, rather than as a passive stage on which the universe unfolds. It's a concept that challenges our everyday experiences and intuition, but it's supported by a century of experimental evidence. So according to Einstein, gravity is not just a force, but the curvature of space-time. Fascinating, isn't it? We've peeled back another layer of the cosmic onion, revealing a universe that's even more intriguing and beautiful than we could have imagined. Now picture the planets as marbles rolling around on our trampoline. What would happen? You see, Einstein's theory of relativity offers a fascinating explanation for this cosmic ballet. Instead of viewing gravity as a mysterious force pulling objects towards each other, Einstein proposed that massive bodies like the sun warp the fabric of space-time around them. Think of it as a marble creating a dip on a trampoline. Other marbles or planets in this case roll along the curves created by this dip, mimicking the orbits we observe in our solar system. This remarkable theory, unlike any other, accurately predicted the bending of light as it passes near the sun, a phenomenon known as gravitational lensing. It also explained the slight shift in Mercury's orbit, something that puzzled scientists for decades. These confirmations of Einstein's theory transformed our understanding of gravity and the universe itself. Gravity, as it turns out, is the cosmic choreographer of our planetary dance. But do we know everything about gravity now? Not quite. In fact, gravity continues to baffle and intrigue scientists. This seemingly simple force, the one that keeps your feet firmly on the ground, is actually the weakest of the four fundamental forces of nature. Yet its influence stretches across the infinite expanse of the universe, shaping galaxies and guiding the dance of planets. Today, researchers stand on the forefront of a new frontier: quantum gravity. This ambitious field attempts to reconcile the principles of quantum mechanics, which governs the smallest particles, with the laws of gravity, which rule the vast cosmos. The goal? To uncover a unified theory that can explain the workings of the universe in its entirety. But this quest is as formidable as it is captivating, a cosmic puzzle that continues to challenge the brightest minds. The gravity of the situation, it seems, keeps our scientists eternally captivated. So the next time an apple falls from a tree, remember the cosmic ballet that's playing out right above your head.